Hello everyone, my name is Eloy de Lera Acedo. I am a researcher at the University of Cambridge, and in this presentation I will talk about the REACH experiment, the radio experiment for the analysis of cosmic hydrogen, and specifically about our experimental approach to detect the cosmic dawn. I'd like to start by showing this slide with the logos of the different institutes and universities that form REACH. The collaboration is led by the University of Cambridge in the UK and Stellenbosch University in South Africa. REACH is being deployed in the Karoo Radio Reserve in South Africa, about 15 kilometers south of the Hera and Meerkat telescopes and the location of the future SKJ-1 telescope. REACH is surrounded by a ring of hills about 200 meters tall, which give us very good shielding from RFI. The outline of the talk is like this. I will start by stressing the importance of systematics and understanding the systematics in global experiments, and then I will explain how we are trying to tackle this issue in REACH. The edges detection that we all know about, reported in 2018, is depicted by this red line here. In yellow we have the envelope of all the physical models known at that point that could predict the signal. Since then, many new models and studies are trying to actually explain things like the depth of the signal, the flat bottom profile, the slopes, etc., etc. We have done some reanalysis of this data. We have, for example, found that if using a flattened Gaussian model to fit the signal, but restricting the foregrounds to physical parameters, we will find a substantially different signal that is even deeper than the one reported in 2018 at center at a different frequency. If instead of a flattened Gaussian model we use a model from a 21 centimeter GM tool, we then get this signal out of our analysis, again both for unrestricted foregrounds and restricting foregrounds to physical parameters. So the goal of REACH is to shine some more light, in this matter, and either confirm or refute this detection. Following from this, I show you here how easy it is to corrupt a 21 centimeter global observation. Very common way to correct for things like the beam chromaticity in global experiments is to use a chromaticity factor made of a sky model and a simulated electromagnetic simulation beam, and divide the data by this factor, in essence, to remove the chromaticity introduced by the beam. In this exercise, we have generated the sky with a GSM map, and we have tried to correct that data with a Haslam map. And what we see here is that the residuals left over in the data can be quite substantial, and indeed potentially corrupt our data and our ability to detect a signal. So in REACH, what we are trying to do is, instead of assuming that our beam or our system is achromatic, we are focusing on explaining those chromatic effects, those instrumental systematics that can be contaminating our data, because we think that ultimately they will be there, and it is essential that we can explain them. So we do a joint Bayesian fit of cosmological models, foreground models, and instrument models using polychord in order to explain the tension between the different models, the correlation between parameters, etc., etc. So our focus again is on explaining all these different components of the signal. So in the REACH system, in order to do this joint Bayesian fitting, we provide data, extra data, in order to do this by having two systems. One is based on a wideband dipole and the other on a very different ultra-wideband log spiral antenna The response of these antennas is of course very different to the sky, which hopefully will also help us trying to understand what can be associated to the instrument and what to the sky, and should be independent of the instrument therefore. Also, these two systems are wideband, 50 to 130 MHz in the case of the wideband dipole, and 50 to 170 MHz in the case of the log spiral, also providing more data for the more information for the Bayesian pipeline. Detecting unknown systematics is very important for us. Our hardware models will account for those things that we can think of, but there will be things that we discover when we analyze the data, and we don't know what they are. So we have developed a very fast tool to detect unknown systematics based on fitting maximally smooth functions to our data with a tool called MaxSmooth that uses quadratic programming. So it's very fast and can be embedded in our pipeline. It uses constraints of the derivatives of these maximally smooth functions so that they should be model very well smooth data such as that expected from the foregrounds, and then expose anything that is not smooth. We have used it with different sets of data. These are two examples with edges and LIDA data showing how we can explain that data with a basic signal model plus a systematic such as sine wave, as well as we can perhaps explain it with a flat Gaussian signal. So in summary, in REACH we do not design our systems to be achromatic. We don't expect them to be achromatic. Instead, our whole design and our whole approach for the data analysis is to explain this systematics effect. We do a joint Bayesian fitting of the cosmological models, the foreground models, and the instrument models. Because we have these many parameters to fit, we also provide more data from two different antennas and receivers that will be observing simultaneously, and in phase one they are a wideband dipole and a conical log spiral antenna. And one thing that I haven't been able to explain in this presentation, but also is part of REACH, is a very comprehensive suite of in-field measurements of our receivers for their calibration. Thank you very much. This is the end of my presentation.